Good morning, Calculus BC. Do you feel it? We are almost done with Infinite Series. This is the last topic for the BC exam. Just maybe a couple other topics for you STC people that I will exempt the non-STC people, just so we cover our bases with that course. But I think I have this lesson. I might want to look at another one related to this lesson. Either way, you guys are so well prepared. Those that have been working on their materials, you're going to do good. All right. Infinite Series, it's in one textbook, it's chapter 8. In our college textbook, I think it's chapter 9. And so I got to make sure of stuff to talk about. Let's represent functions by using power series. And so there's a couple of different kinds of functions, but today we're going to look at geometric power series that represents. It's like the best of both worlds. We've got a power series and it's geometric. Then we can use all the operations that we know about, adding integrals, adding derivatives. It's the same thing by adding polynomials and adding a function as a power series. You know, a power series is the summation as n goes from either 1 or 0, just depends, to infinity, and you have some function here. Well, you can add those together if you have another one. And it's another function. And you can raise a power series to the nth power. Whoop, that disappeared on me. To the nth power. You can raise them to the x power. Whatever operation you can do on one, you can do them to this kind of function as well. Let's talk about geometric power series. First of all, let's review power series. A power series, here is a summation of n goes from 0 to infinity of a sub n times x minus c raised to the n. And it's a power series because my power is changing, and this is n is going to be plugged into like your first term, a sub 0, 0 power. So when I plug in a 0, I get a sub 0 times x minus c to the 0 power, which is a 1. You get a sub 0. N goes to 1. That gives me a sub 1 times x minus c to the first power. Well, that's just a sub 1 x minus c to the first power. Let's do the 2. A sub 2 x minus c squared. So you got the hint, and it continues. That's a power series. A sub n represents a coefficient of the nth term. If you could go all the way to infinity, that's exactly what this thing is, the nth term. Well, nth isn't really infinity. Nth term could be 10th term, 100th term, thousandth term. But when I put the summation as n goes from 0 to infinity, it is the infinity term, if there ever was one. A sub 0 is independent of x. Well, obviously, because x has disappeared. Okay, that makes sense. May be expressed as a function of n. A sub n equals 1 over n factorial. Well, sure. If we actually looked at this power series one other time, a sub n could be a function of x. Power series are useful in analysis, and this is just talking about it being that they are forms of Taylor series of infinity. They're differentiable. In fact, there was a theorem that we didn't really name it, but Borel's theorem implies that every power series is a Taylor series of some smooth function. Every power series is a Taylor. In many situations, the center of the series is 0. So when the center is 0, this particular one had a center that was not 0. It has C. But what if it was 0? Then you would see the a sub 0 plus a sub 1 x plus a sub 2 x squared, so forth, right? Because the center would have been 0. There it is right here. Recall e to the x, centered at 0, was 1 plus x squared over 2 factorial plus x squared over 3 factorial. And the nth term is x to the n over n factorial. And you can keep on going till you get to the last term. But the last term is to infinity. This is adding them all up, even if you could get to the infinity term. Which, if you had them all to infinity, you would actually have the exact function e to the x. If you stop here or stop here, you still only have e to the x is approximately. Because even if you go to the 100th term, that would have been 0, 1, 2, so x to the 100th. Well, that's just, you have to add them up. I don't want to do, e to the x is not that. If you get x to the 100 over 100 factorial, so you have all of them all the way up to here, it's still a good approximation. And here's another one, sine. Remember, we did sine. Here is the nth term. That's what we would consider to be the function. That's f of x is this, okay? But you need a lot of terms. Actually, you didn't really need that many. We had a pretty good approximation around 0 with just those terms here. I recall us using a calculator. These power series are examples of Taylor series. They're all Taylor series. Geometric series. Remember, you got a series that's 1/2 plus 1/4 plus 1/8 plus 1/16. What makes it a geometric? Geometric is if you take any term. Let me go to this term, 1/16, and divide it by the one before it, 1/8. Lo and behold, you get 1/2. Well, just take 1/4 and divide it by 1/2. What do you get? 1/2. It's a constant ratio. Geometric series are among the simplest examples of infinite series with finite sums. Finite means you can always add up a geometric series. It's always the first term divided by 1 minus that ratio. So in this case here, if I had this all the way to infinity, all the way, it adds up to the sum to infinity would be the first term, 1/2 over 1 minus, oh, this one doesn't work that way, does it? 1 minus r. Yeah, that doesn't look very good. So because I would get 1/2 divided by 0. So what we do is, who said I have to start at 1/2? Let's start at 1/4. And then I'll add the 1/2 in a second. So that sum would be 1/4 over 1 minus 1/2. 1/4 divided by 1/2 would be times 2 over 1, which is 1/2, plus, I should have wrote it as it's equal to this plus the 1/2. So plus the 1/2 plus the 1/2, it adds up to 1. We've talked about that before. Historically, geometric series played an important role in development of calculus, and they continue to be central in the study of convergence of series. Geometric series are used throughout mathematics in a lot of stuff. Okay. Remember that if the absolute value of r is less than 1, it always converges. So we'll always get that sum. But if the absolute value of r was greater than 1, it diverges. So you wouldn't get a sum because it keeps on going forever. All right, let's put these two beautiful things together, geometric and power series. So I'm going to start out with a 1 over 1 minus x. Now, this looks like the sum of something. If you say, I want to add it up, this looks like the sum formula, doesn't it? A sub 1 over 1 minus r. Can you see that? I mean, I don't even have to really work it out because I just gave you that formula a minute ago. Your first term, a sub 1 over 1 minus r, is the sum to infinity. The sum to infinity of something. Well, what's that something? Okay. Well, look here. R is x. My first term had to be a 1. So if I start with my first term as a 1, how do you get to the next one? I will refer you back to that last problem. 1 plus 1/2 plus 1/4 plus 1/8. How do I go from 1/2 times 1/4 or plus 1/4? You have to divide it by 2 each time. Or it was the same thing as multiplying by a half because r was that common ratio. So 1/2 times 1/2 gives me the 1/4. 1/4 times 1/2 gives me the 1/8. So r was 1/2, remember? So to get to the next term, you multiply by r. To go backwards, we find r by dividing them. That's how we get the r. Anyway, so if r is x in this problem, then 1 plus multiply 1 times x, that gives you x. Plus, take x times an x, that gives you x squared. Take x squared times x gives you x cubed. So what you see here is 1 plus x squared plus x forever. How do I get this piece here is the question. Well, that's easy. Because generically, when we go 0 to infinity, we are always taking my original first constant, a sub 1, times r. I should say a sub n, because the first one was a sub. Now you might be asking yourself, how is that equal to the summation of x to the n? Well, plug in your first one. Plug in x is 0. N is 0. X to the 0 is 1. X to the 1 is x. X to the second is x squared. So I'm missing my exponent right here, r to the n. A sub 1, r n. So starting with a 1, x to the n. So this is your first power series represented as it was the sum of an infinite geometric series. Okay, so here's the same thing I told you about. Recall that, or so we had this before. We just didn't think about it. Probably, maybe didn't make that connection, and that only works if it's convergent. So the opposite value of r has to be less than 1. Obviously, if it diverged, it wouldn't have one. What else are we doing here? Oh, instead of looking at r, we knew our function had to have an x in it. That's why, well, because we were looking at it. So that's the substitution I made. So the function was 1 minus x as the denominator. That's merging the two beautiful things. Are you ready to do one? That's the same one. That's the same problem. Why do I have it there twice? Is centered at 0. Notice this, 1 plus x minus c, which is 0, plus x minus c squared. That's so you see the problem. Remember about a power series always has a center. This one obviously, well, the one we just wrote in my graph, my center was here at 0. So I could do my radius of convergence and find out that I have this interval here that works out really, really, really super well. Matter of fact, if you did your radius of convergence, you would, well, that's easy to do. Let's see, we had a sub n x to the n. That's just a constant. So x sub n r is convergent when it's less than 1. That means x to the n is less than 1. And x to the n is greater than a negative 1. Nth root both sides. The nth root of 1 is x is less than 1. And nth root both sides, you could get to the negative 1 if it's an odd nth root, but greater than a negative 1. That's going to be the best I can do with it. So we have our intervals negative 1 to 1. Greater than negative 1, less than 1. That's exactly what you have here. Negative 1 to 1 is my interval. And the radius, since that distance is 2, radius of convergence is 1. And there's what he showed you as a domain. I didn't check the endpoints. I did have a problem at the negative 1, as you recall. So 1's not a problem. This side was okay, but this side was not. So that's how I get the parenthesis instead. I had an issue because n could possibly be even, and you can't take the even root of a negative number. So there is the same problem we just talked about. Picture. If it's centered at negative 1 instead, then I can go back and forth this way. See what's happening. You can rewrite this series. Instead of centered at 0, what is the function centered at? what if, here we have it centered at 0. Oh, what if we want to make it centered at -1 instead? Because look at -1. Let me show you how to do this. We already have this one centered at 0. If I want to center this at -1, do I write on this or do I have it as a slide? Okay, I'll just take this slide. So instead of -0, I want to have it minus a -1. But I can't just go and say, oh, x minus -1, and just do it to one side. I need to balance out that denominator, so I haven't really changed it. I'm just changing the way it looks. So if I'm adding a -1 here, and technically this minus meant that I was really subtracting, and I'm going to add 1 to cancel it out. And if you think about it, minus -1 is a +1. This negative in front made it really a -1. So now I'm adding 1 to over outside of the parenthesis to balance that out. Okay, so once I balance that out, look what it looks like. It looks like this: 1 over 2 minus, I'm going to write it as x plus 1 for now. Okay. But that form is still not right because I need this term here to be a 1. Because I need 1 over, or I don't need to have a 1, but I mean, that's what it started out as. I need it to be an a sub 1, some number. It doesn't matter what number it is. But this has to be a 1 minus the r. Okay? This has to be true, no matter what, these two things. So I'm manipulating it again. I got my centered to be my x minus -1, so that part's accomplished. But that's not a 1. So I have to say, what if I divide every term by a 2? Divide by a 2, divide by a 2, divide by a 2. I'm starting to see something happen. I now have a 1/2 on top, 1 minus all of this over 2. That looks pretty good. That looks really super good. I can actually start talking about a sub, my first term, a sub 1 must be a 1/2, and my r must be x plus 1 over 2. You see where I'm going with this? And every power series, n is 0 to infinity, must be my a sub n times my r to an n. So you see where I'm going? A sub n, let me, a sub n, summation, n is 0 to infinity. R is x plus the 1 over 2 to the n. That's my geometric power series. And it'll look like this if I want to let n be 0. Well, that gives me a sub 0, x plus 1 over 2 to the 0 power, all goes to 1. It's just a sub 0. plus n is 1. That gives me a sub 1 times x minus 1 over 2 to the first power plus n is 2, a sub 2, x minus 1 over 2 squared plus n is 3, a sub 3, those are just constants, x minus 1 over 2 cubed, and it continues to the general term, a sub n, x minus 1 to the n over 2, and it continues to infinity. So let's see what it looks like. It's more simplified. A sub 0 plus I could pull out that half if you wanted to. A sub 1 over 2 times x minus 1 plus a sub 2 times x minus 1 squared over 4, because 2 squared, plus a sub 3 over 8 x minus 1 cubed, plus, let's do one more just for fun, a sub 4 x minus 1 to the 4th over 2 times 16 plus, and I think that could be this. Let me go to the next slide and see if I nailed it or not. I did lose my 1/2. I knew my 1/2 has to be part of the answer in my series here, because it should have been a. It is an a sub 1, so I need to have a 1/2. 1/2 right here in front of everything. So how does that change my answer? A sub 0 is going to be the 1/2. Then I'm going to have a sub 1 over, this becomes, everything is times 2 in the denominator. Of 4x plus, these are all pluses, what did I end up, minus, minus. I see it. A sub 2 over 8. A sub 3 over 16. X plus 1 to the 3rd. So forth. Okay, let's see. 2, 4, 8, 16. We'll double check. Let's see. I was doing all this, trying to lead you through the manipulation. I needed this. See, what did I do here? I had my 1 plus 1 is 2, and then, okay, I had that. Anything else? And I continued again. I had more room to work. But let's get to the nitty gritty. Let's see. Divide everything by the 2, and therefore, let's see. I have R is, did I? A is, I don't know, my A sub 1, obviously, well, I called it A here. should be a 1/2 instead of a 2 because I fixed it all. R was all of this. I don't think it's just this. Let me see what the next slide says. These are all the steps. Okay, here's my answer. Yep, I have that. If you think about it, the 1/2. Oh, I lost my 1/2. That's where I went wrong. Let me back up. Did I? I don't know if I even wrote them out. Oh, I see what he did. I did mention that we could factor out a half. There's your 1/2. There's your x plus 1 over 4. There's your x plus 1 squared over 8. There's your x plus 1 cubed over 16. There you go. And the r, I told you, absolute value of r has to be less than 1. And I told you that r was the x plus 1 over 2. I did tell you that. So if you say the absolute value of x plus 1 over 2 has to be less than 1, how do I solve that? X plus 1 over 2 could be less than 1, and x plus 1 over 2 could be greater than negative 1. Multiply both sides by 2. X plus 1 is less than 2. X is less than 1. X plus 1 is greater than a negative 2. X is greater than a negative 3. So you know we're looking between a negative 3 and a 1. And so that's a distance of 1, 0, negative 1, negative 2, negative 3. That interval is negative 3 to 1. Your radius is 2. Did I miss anything? He hasn't defined it there, but that's going to give you the same values. Let's see, did he do anything else on the next slide? Converges on this interval. That's the interval of convergence. It's the same interval I have. That was fun. Let's do another one. Find a geometric power series centered at 0. Okay, that's easier. When it's centered at 0, you don't have as many manipulations. We're using 4 over x plus 2. Now remember what we want. We want to create the a sub, he called it just a, but it's actually a sub 0. It's the first term, over, or a sub 1, depends on what you're counting by, 1 minus r. Right away, I can change this to 4 over 1 x plus 2 to be, my r has to be a function. So I got to change that around to 4 over 2 plus x. Now I need to put a minus in here. So I'll write that as 4 over 2 minus x. And so you can see that it's coming along really nice. I need to have a 1 here, so divide everything by a 2. So that's still equal to now a 2 over a 1 minus a negative x divided by 2. And I found out that my 2 is my first term. So you're mark my words, 2 is my first term. How do I turn that into my power series? Power series, n is 0 to infinity, of my first term, or a sub 1 or a sub 0, whatever you want to call it, times my r to the nth power. In this case, I know r is equal to negative x over 2. That has to be r. So equals to my first term 2 times negative x over 2 to the nth power. And that is correct. But I'm sure the author will probably do this, if I remember, that negative 1 can be factored out to the nth power. So I have a 2 and a negative 1 to the nth power. Then I have the x over 2 to the nth power. And we're also going to want to talk about the interval of convergence. So the absolute value of r has to be less than 1. So the absolute value of negative x halves is less than 1. The absolute value switches the negative anyway. So it's the same thing as x over 2 less than 1. So that gives me x over 2 is less than 1. And x over 2 is greater than a negative 1. That means x is less than 2. And x is greater than a negative 2. Do you see the interval? Negative 2 to 2. Okay. And that's zeros in the middle. So your radius is actually 2. So there's my interval. Let's see what it looks like if I break it down. If n is 0, here's what I'm going to do. If n is 0, negative 1 to the 0 is a 1. X over 2 to the 0 is a 1. 1 times 1 times 2 is 2. Told you it would be a 2. Plus, n is 1. Now, if n is 1, that's negative. So let me erase my plus sign for this first term and definitely put minus. What is that going to give me? If n is 1, it's still going to give me x over 4. Now when n is 2, it's even, so it's going to be plus x over well, no, that doesn't change, does it? It was x to the n. What am I doing? X to the n. That's why I got confusing. When it was a 1, it was x over 2. When it's a 2, it's going to be x squared. This one didn't change. This is just an x. When it was a 1. Yes, that's right. There you go. Make more room. 2 minus x plus x squared over 4. When n is 3, it's minus again. X cubed over 8. Do you see the pattern? Plus x to the 4 over 16 minus x to the 5 over 32 plus. You got the pattern? Let's check it. Let's check everything. Well, there's my first term. There's my r. Looks good. He factored out a 2. But let's just put it back in and see if it works. 2 minus x plus x squared over 2 minus x squared over 4 plus x cubed over 8. It looks good. Doesn't it look good? There's his convergent. Implies from -2 to 2. Haha, I love it. Not too bad. Operations with power series. A lot of gobbledygook here. Just basically talking about that you can, if you have two separate power series that are both geometric, obviously, it doesn't really have to be both geometric. Doesn't matter any kind of power series, that you can always multiply a constant to your x. And if I'm just doing f, and f was this one, it's just going to be an a times the constant times x to the n. If you were taking your x, it's that composite now. If you're taking your x and raising it to the nth power of f, well then x to the n to the n. That's what happened here. X to the n to the n. You're just applying it to the x power. It doesn't really matter. You can add or subtract two different power series. And since it's x to the n and x, since this part was the same, it didn't have to be. In this case, it was just lucky. He could have just wrote equals a sub n x to the n plus b sub n x to the n. Because what if they were different? But in case this time they were the same, he factored out x to the n, leaving a to the n plus or minus b to the n. Doesn't matter what you're doing. How do we use it? Find a power series. So I'm assuming we're going to be adding two. He even says that. Find a power series for this. Now, this doesn't look like it's geometric. It doesn't even look like I could make the top into a constant. But it looks familiar to me because if you were looking at me, I'd ask you guys, that's a difference of squares. This looks like 3x minus 1 over x plus 1 times x minus 1. And then I'd be asking you, class, when have we seen this before? And I can hear you saying right now, well, at least maybe it's Sandy being real loud. Partial fractions. Oh, yes, you're right, Sandy. Partial fractions. So remember how we did partial fractions. We take the numerator and break it up into a over one of the factors plus b over the other factor. Cancel out all the denominators because we're going to multiply both sides by x plus 1 times x minus 1, and that cancels everything. So you're really looking at, do you remember this? 3x minus 1 equals a plus b. And then we say to ourselves, actually, it's not that. It's going to be a. I messed up. But you know what? I can't go anywhere with you guys. Somebody's always messing up. A times x minus 1 plus b times x plus 1. There, okay. What do we do next? We substitute some values of x's that help us solve a and b. So if x is equal to a 1, I know this will all go to 0. So plug it in. 3 times 1 minus 1 will have to be equal to b times 1 plus 1 That's 3 minus 1 is 2 equals to 2b. B is 2. Now, if I plug in x equals to a negative 1, this will go to 0 because negative 1 plus 1 is 0. That will leave me 3 times a negative 1 minus 1 equals to a times negative 1 minus 1. That will be negative 3 minus 1 equals to a negative 2a. That's a negative 4 equals to a negative 2a. So a is now equal to 2. Does everything look okay? Heck no. Look at that's a 1. 2 divided by 2 is a 1. So this can be written as 2 over my x plus 1 plus 1 over x minus 1. Which, look at it. Those are two beautiful rational functions that could be turned into geometric power series. Wow. So f of x is 2 over x plus 1. G of x is equal to 1 over x minus 1. And we are adding them together. So let's handle them separately. And so, okay, this is fun. We just did that. We just did a whole bunch of these. I have faith in you. I can stop this now and you'll figure it all out. This one here, the only thing missing is I need a minus r. 2 over x minus minus 1. There it is. Oh, wait a minute. Hello. X can't be on that side. I needed to rewrite this to 2 over 1 plus x. And now rewrite it as 2 over 1 minus minus x. Oh, I feel better. I knew something was wrong with the force a minute ago. That power series is summation n goes to 0 to infinity. My first term is a 2. My r is a negative x to the n. Nice. Let's do g of x. G of x is already done. Is it? It looks like it because there's a minus. I got to switch those around again. Negative 1 plus x. It's not done. But that's easily turned into 1 over negative 1 minus minus x. And then there's my r here almost, except for I don't want a negative 1 here. So I divide everything by a negative 1, including that term. So I'm left with a negative 1 on top, a 1 here, minus a positive x. So in this case, this g of x is really the summation as n goes to 0 to infinity of my first term, which is a negative 1, times my r, which is x to the n. All right, stare at that. Eat your heart out. All right, what did I want to do? I was originally wanting to add the f and the g. So f of x plus g of x will be the power series as n goes to 0 to infinity of a 2 to the, no, negative 1 to the n, x to the n, plus summation, n is 0 to infinity, of, that's a negative 1 times x to the n. And do you see what I see? Both of these have an x to the n. So if I put them together with 1, let me first do that. Together, they become a summation as n is 0 to infinity of a 2 times negative 1 to the nth, x to the n, plus a negative 1 times x to the n. Factor out the x to the n. That's what he did in our sample, just for kicks. He put the x to the n on the outside, factor it out. That leaves me 2, negative 1 to the n, plus a negative 1. Can I do anything else with it? Looks like about as simple as I can do. So let me start building it. Equals to, this is what it looks like. If n is 0, negative 1 to the 0 is a 1. 2 times 1 is 2. 2 minus 1 is 1. X to the 0 is 1. So that give me 1. If n is 1, negative 1 to the 1 is a negative 1. Negative 1 times 2 is a negative 2. Negative 2 plus a negative 1 is a negative 3. Negative 3, x to the 1, x. If n is 2, negative 1 squared, still 1. 2 plus a negative 1, still a 1. X squared. That's weird. I wasn't expecting that. Let's go n is 3. I know I'm going to have an x cubed in there, so let me see what happens. 3. Negative 2 plus a negative 1. It's a negative 3 again. Wow. So the next term we're going to have an x to the 4. So if n is 4, that becomes a positive 1 again, times 2 is 2. 2 minus 1 is still 1. It turns out just to be plus. So do you see a pattern? Every odd number gets a negative 3 coefficient. Every even number gets a 1 coefficient. I don't know if that's right or not. I'm dying to find out. There's a lot of work here. Beautiful work, if it's right. Partial fractions. Sandy, you were right. And here's my F. Here's my G. Only thing I didn't do was do my intervals. Oh, man. Well, you got to. So I just had to say x to the n, absolute values, less than 1. That means x to the n is still less than 1. And the other part was, and x to the n is greater than a negative 1. So that gives me, if I nth root both sides, x is less than 1. If I nth root both sides, sometimes x will be greater than a negative 1. Sometimes. So he's probably going to do this business with me. Yeah, Definitely this and this probably. What did he do? If he does it at all. Oh, there. Well, that's just the f. But it has to be both. So if I do this, absolute value of x is less than 1, x is less than 1, and x is greater than a negative 1. They have the same values. And since you can't be a negative 1 on the 1, he just left them both open. So left them both open. Makes sense. That looks good. That's the lesson, guys. Now, what I do have here is, let's see, that's not part of yours. Where was the lecture? In these notes, in the BC workshop materials, we started out, this is again, geometric power series, was talking to you about what it meant to be a Taylor series. And he just gave you a Taylor series. I went and talked to you about that this can be written as geometric. And if we're centering it at 0, it's Maclaurin. Taylor is NEC, including 0. So this is a problem that very similar. We'd have to manipulate it. 1 over 1 minus x. What am I doing here? That's silly. No, I don't. It's already done. There's your r. So that really very simply turns into n is 0 to infinity of the first term is a 1. Didn't have to do anything. X to the n. First 4 terms, 1 plus x squared plus x cubed. And does it, he wants to know where it converges. Well, that's simple. It converges when absolute value of x is less than 1, which if you were to finish it out, x is less than 1 and x is greater than negative 1. Use your answer in part A to find the Maclaurin series for, okay, killing 2 birds with 1 stone. If this is f, then f prime of x would be, check it out, summation as n goes to 0 to infinity of the derivative. It's n times x to the n minus 1. Take 1, multiply it by the exponent, take 1 away. And it should give me, let me do it with taking the derivative of each of these terms here. Derivative of 1 is 0. That's not a non-zero term. And, he did say find the first non-zero terms and the general term. So back up to here, I probably could have still added plus dot 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 plus x to the n plus dot dot dot. Anyway, 0 is a derivative of 1, and 1 is a derivative of x, 2x is a derivative of x squared, 3x squared is a derivative of x cubed. I do need to go one more. 4x cubed plus dot 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 plus n x to the n minus 1 dot dot dot. Now, if I was right, this general term should give me the, or this general term should give me the same thing. Let's see if it works. If n is 0, I get 0 times x to the negative 1 power. That's 0. Plus, if x is a 1, I get a 1 times x to the 0. That's x to the 0 is a 1. If n is 2, I get 2 minus 1. That's x to the 1 with a 2 here. 2x. If n is 3, 3 minus 1 is x squared, 3x squared. N is 4, 4x cubed. It works. I can do it from either the terms or I can do it from the individual function. All right, use my answer in part B to find the sum of the infinite series. My answer to part B, I'm not really sure how that's related. I'm going to be honest, you're not using B to do this. And if I wanted to find the sum of this infinite series, I would first check to see if it is geometric. What times 1 is 2/3? 2/3. What times 2/3 is 3/9? Let's see. Well, it's easier to do this. 3/9 divided by 2/3 is 9. 3/9 divided by 2/3 is 9/18 is 1/2. That's not geometric. 4/27 divided by 3/9 is 36/81. That's divide both by 9. That's 4/9. That's 4/9. So I had 2/3, 1/2, 4/9. I don't understand this one. I think I understand what they're doing. You had to realize the terms are related to this series up there. But I'm going to need more time about this. Oh, wait, this was it. Next page. Write the Maclaurin series for F. First 4 non-zero terms in integral term. For what value? Okay, we've done this one. We've done this. We said this is R. Absolute value of R is less than 1, so that means we're between -1 and 1. Okay? And we know that F is not, F cannot equal to a 1. X can't be a 1. So definitely it's a parenthesis here. Now, the argument could be I could use a 1, but I don't think that's even the issue. So f of x is summation n is 0 to infinity. First term is a 1 times the r, x to the n. As I recall, remember this one? Was a 1 plus when x is a 1, it's an x. When x is a 2, it's x squared. X is a 3, it's x to the 3 plus the general term, x to the n. And we know that absolute value of r has to be less than 1. And B, use the answer to A to find the integral of f of x. So the integral from 0 to x of, basically, it's the integral of the summation as n goes to 0 to infinity of x to the n. Well, I'm going to do it term by term by term. If I integrate 1, that's an x. If I integrate x, that's an x squared over 2. If I integrate x squared, that's x cubed over 3. If I integrate x to the 3, it's x to the 4 over 4. And then those are 4 non-zero terms. If I integrate x to the n, that's x to the n plus 1 divided by n plus 1, so forth. Where does this converge? So it converges when x to the n plus 1 over n plus 1 absolute value is less than 1. So that tells me x to the n plus 1 over n plus 1 has to be less than 1. And x to the n plus 1 over n plus 1 has to be greater than a negative 1. Multiply both sides by n plus 1. I get x to the n plus 1 is less than n plus 1. Take the nth root, n plus 1 root of both sides. That gives me x is less than 1. Because the n plus 1 root of n plus 1 is the same thing as saying the third of 3. Oh, wait, it's not the same. Well, it did cancel out over here. I'm going to call their bluff. And one thing I did notice that I didn't do right. I was supposed to take all of this. Let me put it in red. All of this from, it was supposed to be a t here. Let me fix it up. Going from 0 to x, which means plug in the x and then plug in the 0 and subtract. So you're going to get the same answer I just had. This was supposed to be f of t. F of t was equal to, yeah, I wrote that right here, but I didn't. Summation, no, I didn't write it here. Should be t to the n. Anyway, when I integrated, I did get a, oh, that was the integral. I got x plus x squared over 2 plus x cubed over 3 plus x to the 4 over 4 plus x to the n plus 1 over n plus 1. And I was trying to do the interval, but I'm going to erase that. This is true. This is true. But I'm going to stick with the same interval of convergence I had up at the top. That the interval was x could be, as I recall, let me look at what I had here. X could be a negative 1, but could not be a 1. So negative 1 to 1. I'm going to keep the same thing here. And I'm going to stick with it. One more here, real quick. I don't know if I can do this one or not. Use your answer and probably find the sum of this infinite series. I could only find the sum of this infinite series if it is something I can identify. Look at the terms. 1/3 plus 1, 9 times 2 is 18, plus 27 times 3 is 81, plus 81, plus 3 times 3 is 81 times 4, 244, 1 over 244. And obviously, I could continue that. Now that I'm looking at this, the problem that I scratched off on the other, do them. And I need to get this saved and set to the cloud for you to try to get working. And I'll put a second video up later on today, doing those two problems. I think I have an idea how to do them. But what I need you to look at is, let me get out of all those things. There was the problems, the worksheets. Do as many of these as you can. This one looks like we've done this before. This one you should be able to do, no problem. All of these. Remember, this one is C is a 1, so you're going to have to manipulate. I'm going to need an X minus C. I'm going to need to see an X minus a 1 in the bottom down here. So you got to manipulate that. This function is a typical free response problem. We've done this already. He's taking derivatives. Okay, interesting. I do want you to do these 3 problems. They're AP-ish. I think you can, and granted, guys, there's no secret where they're at. But if you just copy, I'm gonna know it. Oh, here it is. And there was another one. Yeah, they're all good problems. Work them out. Submit them to me. But I'd rather see your real work, and I'd rather see where you went wrong. If you find your own answers, show it to me. Okay? I'm going to save these. I'll come back to you later on and try to talk about those other 2 problems. Nothing I saw in these problems were jumping the leap like they were doing. So, talk to you later.